This is the tutorial on chapter 9. During tutorial 10, we had a quiz, so I'm covering this offline. So if you have any questions, feel free to contact me. So I'm going to start with a brief introduction, and we're going to go through 3 questions. So chapter 9 is all about natural convection. So up until now, we've been studying kind of airflows that are defined. So particularly with forced convection, it would be something like a fan that's driving the wind over a plate. But the differences here is in natural convection, we're relying on the buoyancy forces of the air. So for example, in this case, we have a hot surface here. The hot surface would cause airflow upwards because we all know hot air rises. As it does this, it creates quite a similar case as before. So we get this boundary layer, and the boundary layer kind of gets thicker and thicker the farther it goes up. So effectively, for problem solving, what this means is we have a kind of new set of equations and new set of situations that we need to deal with. So again, comparing to forced convection, we had flat plates, we had round objects, then we moved on. Then we also had internal convection. So each case has to be treated with a different equation. It's a little tedious and a lot to write down, but the idea is that the airflow is quite difficult to model, and it's not easily made with simple equations because airflow is like that. A lot of molecules all moving around randomly, and we generally take averages. So all of these equations are formulated empirically. And so I've just included a table. This is kind of one example of something you would use to decide which correlation you would be using. So this is natural convection over surfaces, and you can see here we have quite a few surfaces. So we have flat plates, we have inclined plates, all of which are different. We have vertical cylinders, horizontal cylinders, and then this one is interesting, and it's actually going to be the answer to our first question. So you can think that if you had a plate, the way natural convection happens on it is actually different from the top and on the bottom. So on the bottom, you have this hot layer, and it's causing airflow upwards because it's pulling in this cold air. And so your boundary layer is kind of going to be compressed by the way the airflow happens, versus on the top, you have it rising. And your boundary layer is going to be a little bit larger. So again, just give you some intuition as why you actually need different equations for all these cases, because we are talking about the buoyancy force. And so even something like it being inclined makes quite a difference. So the way you're going to go about solving these is quite similar to before. So you're going to look up all your properties on table A15, and generally you'll need your K, your viscosity, your Prandtl number. And then we're actually going to do one more, or let's move on from this. So once you've gotten those things, now rather than going right ahead and calculating it, we're going to need this extra thing, and you'll see it in these equations. It's your Rayleigh number. So your Rayleigh number, this is our relationship between buoyancy and viscosity. So intuitively, it makes some sense that we care. However, the forces that cause it to rise are in relation to how willing the fluid is to flow. And Rayleigh numbers are calculated using gravity. Again, makes some sense intuitively that that's involved. Our surface temperature minus our infinity. Our characteristic length, and we'll do a couple of examples of those. Our Prandtl number. By our viscosity. And so the only term here that's a little new for us is our beta. And our beta So our beta for ideal gases, which we're going to model them as in here, is going to be 1 over our bulk temperature. And we've calculated this bulk temperature before. And same temperature you would be using to calculate these. And this is a measure of our buoyancy forces. Okay, so we'll get started. So like mentioned, our first question is quite similar, or quite simple. It's just theory. We want to consider laminar natural convection, the ventilation of a hot plate. Will the heat flux be higher at the top and at the bottom, and why? And I think we've already gone through this, but essentially your boundary layer is going to be thinner than at the top, just by the way the convective forces work. And so we're going to actually get more heat transfer from the top. And so what's the way it's written is heat flux will be higher at the bottom plate. Heat flux will be higher, sorry, more heat flux at the bottom plate, since the thickness of the boundary layer is lower at the bottom, or is smaller at the bottom, which is a measure of thermal resistance. So this thickness is a measure of thermal resistance. So I'll just quickly make a note. Okay. And just so we can bring it back practically, so the quiz you guys will have just done during the session, it was cooling of chips. And so we had airflow here, and we know that our boundary layer starts and then develops. And we found, or we should have known, that right at the end, this is going to be our kind of area of worst heat flux. And this is kind of happening for the same reason. As the boundary layer develops, this becomes quite thick, and we have more resistance to heat, being ejected into the environment, which in the case of cooling a chip is what we want. Okay, we'll move on to question 2. All right, and this question refers to a steam pipe. So we have steam going in. We're not actually going to look at the steam going in. That would be kind of a chapter 8 thing, internal forced convection. But we're looking at how much heat is being dissipated on the outside. So we have this air on the outside. It's 45 meters long. We know the thickness. We say that the average temperature of the outside is 100, of the outside of the pipe is 170, and the temperature is 20, so room temperature roughly. The outer surface of the pipe appears to be oxidized and has an emissivity, and the surrounding surface temperatures are 20 degrees. So this one, we're going to have 2 forms of heat transfer. We're going to have our Q due to convection and our Q due to the radiation. And the radiation, we'll be looking in more detail in the next chapter, but for now, chapter 1, we already covered the kind of basic calculations. Not sure what happened to that 45, so I'm going to add that back in. Okay. So we'll move along and we'll do the process I described. Oh, and just there's one part at the end that asks us to calculate the cost of the heat that's being lost. So we have our dollar per therm, and then we have therm is equal to kilojoules. So we're going to be able to find our heat loss in kilojoules. We'll be able to convert that to dollars, and we'll get to that. But first, let's look specifically at the natural convection. So the first thing we're going to do, table A15, we're going to find our bulk temperature at that average. So between 170 and 20 over 2. This is equal to 95. So we're looking at our properties at 95. Viscosity is 2.2. And our last value, this is the new one. This one's going to be 1 over our bulk air temperature. And we specifically want this in Kelvin. So we're going to do 1 over 95 plus 273, which is 0.002717 Kelvin to the -1. So as usual, the way to know if you need it in Kelvin or Celsius, I think in this case it's quite obvious. But the general rule is if you do it in Kelvin, you do it in Celsius, and you get a different answer, the Kelvin one is correct. Usually we say it's the difference, but we've seen a couple cases where it doesn't look like a difference in temperature, but in fact it actually is. So it's always nice to get familiar with which cases you can leave in Celsius or Kelvin. So moving on from that, now we're going to calculate this buoyancy calculation. And I'll just make a note here. So this is our characteristic length for our cylinder. So our LC is equal to our D. Our diameter was given in centimeters. Yes. Okay. Okay. So we know our gravitational constant, 9.81. We know our beta, we just calculated that. Viscosity we got, diameter is here, and we know our surface temperature, and this should be T infinity. So from that, we can calculate our Rayleigh number, which is 1.229 times 10 to the 6. Okay, and now what we need to do is we need to determine which correlation we are taking. So we would go to that chart, we say we have a horizontal cylinder, and then we have an equation for that. So again, it's just a matter of knowing where to get the equations from. All right, and again, this is all squared. Okay, so I won't write out all the equations, but we got this off our table 815. We just calculated that, and everything else are just numbers. So this, we're gonna go to calculate as 15.41. Okay, now of course we know that our Nussbaum number is related to our H. So usually we say Nussbaum number is equal to dH over K. Rearrange that, we get K over D, Nussbaum number. So this one I'll write out because it's a little shorter. Sometimes it's nice to see the numbers. Okay. And then one thing that'll be useful for calculating our final Q is we'll just get our area calculation out of the way. pi dl. All right. And finally, we're going to calculate the total energy we're losing. So our Q dot is equal to HA delta T, Ts minus T infinity, back to that equation we did in the first chapter 1. And then we're also going to make sure we want to add our radiation here. So this was emissivity, surface area, Stefan Boltzmann constants, and then this time we're going to take our Ts minus T surroundings. Okay. So we know our H, we just calculated, and our A, our Ts and T infinity. So our T infinity in this case was 20 degrees Celsius. Emissivity, we were told, was 0.7. We know our area. Our Stefan Boltzmann constant is a constant that can be easily looked up, and it's this nice 5.67 times 10 to the minus 8, 5.5678. And then just one more note I'll make about this. Our surroundings and our infinity are not the same temperature. So in this case, we were told that actually, they're not always the same temperature. I'm going to have to remind myself for this question. Okay, so in this case, taking the surrounding surface temperatures at 20 degrees. So my mistake. They are the same temperature in this case, but they don't necessarily have to be. So this will also be 20 degrees Celsius. Okay, all that calculated out, we'll get 20.5 kilowatts. Okay, now the second part of that question, which was just how much money we're going to be paying. So the Q, and actually Q of our gas, I should say. So we're putting energy in using gas, and then let's take a quick look at what it said here. So our gas has a furnace efficiency of 78%. So not all of the, so we're going to lose a little bit, 78% of it, just in the furnace. And so what's being lost out of this pipe is is already lost about 78% from the furnace. So we're going to incorporate that in. And actually, we're going to calculate our total amount of gas. So this is our rate of heat transfer of the pipe, the amount of time we're talking about, divided by our efficiency. Kilojoules per second over our 0.84. And I'm just going to do one more check. Okay, so it seems as though this question's from a slightly earlier version of the textbook, so this should have been 84%. Okay. Lots of jumping up and down. Okay, so we have this, and then we're gonna convert it into therms because that's what our price was. And then they wanted us to find our yearly price. So we have the seconds here, we're just gonna convert that to years. Okay, all that said and done, we have 7308 therms per year, which is a weird unit, but it makes sense now because we know that our cost is $1.1 per therm. Multiplied by our 7308 therms per year, and we get our yearly cost. $6 per year. Okay. So that's the end of this question. So there was a little price thing, but again, the general workflow of the question was pretty straightforward. We got our properties, we calculated our Rayleigh number, we found the correct nuisance number correlation. We use that to calculate our heat transfer coefficient, and then we use that to calculate our heat loss. And we're going to do a similar thing in the next question, but the next question just has a little few more cases involved with it. Okay, so in this question, we have a double pane window. We know the heights and widths. We know how much the air gap is in between. And we know that the room temperature is, we know the room temperature is in the inner glass temperature. So this is kind of a weird question. I don't necessarily think it's worded in the best way. So one of the things we're going to do here, which looks a little weird, is we're going to actually ignore the conduction that happens through the glass. So they say the inner pane of the window, and if you look closely, it looks like the arrow is kind of pointing here, but actually what they mean is both sides. So this side is 18 and this side is 18. And same with here. So in the end, what we're going to try to find is the okay, this doesn't really say what we're supposed to find, but I can just tell you, we're going to find the temperature of the inner glass. Oh, sorry. Determine the temperature of the outer glass layer. So it does say my mistake. Determine the temperature of the outer glass layer and the rate of heat loss through the window. Okay, there we go. And so at first, this question looks a little strange because we don't really know. This is the outside. We don't really know what the outside temperature is. And so it seems weird that we could know what this temperature is. But I mean, one of the initial assumptions we're going to make is that it's steady state. And so what steady state means actually is that, so we know this temperature, this outside room temperature, we know is glass temperature, and knowing what we know now, we know it's kind of air, and it's going to have natural convection here. So we can calculate our buoyancy, and we can actually figure out this heat transfer that's coming from the air here. Because it's steady state, whatever this heat transfer is actually going to be the same all the way through the window. So that may be a nice way to, it's a kind of a nice problem solving thing, because there could be a case where you know these two temperatures, and you can then, because you know that heat transfer is constant through this material, you can find your total heat transfer, assuming that you're considering steady state. And then the one thing I'll add before I go ahead and solve this problem is, just as from a practical point of view, there's this kind of cool phenomenon that happens with these windows. Probably worth sharing because this is building engineering, which is that the wider your gap, there's kind of an optimal gap of between a window, because if you have a really small gap, the air has a little more a harder time kind of circulating around. And so by this having a small gap, you're restricting the natural convection that wants to happen in the inside. But what you're also doing is making it so that these two windows are closer together, and so there is going to be a little bit more heat transfer associated with their closeness, but a little less associated with the fact that the convection happens. As you widen it, you're allowing more convection, but you're also creating more distance. And so if you ever look at a graph of what the optimal thickness is, it actually has a peak. So if you look at the resistance versus the thickness, the graph will look something like this. So there's an optimal thickness where you're restricting convection well enough, but you're also giving the window enough space. So just an interesting fact. But broadly, this question is going to have pretty much the exact same strategy, where we're going to find our properties, find the right equation, and then when we do the second one to find this internal wall temperature, we're actually going to be using a different set of equations, or a different equation, because this is not the flat surface case, this is an internal surface case. So that's a lot of preamble. Let's get into it. For this first one, we can call this kind of heat transfer 1. Our bulk temperature is that's the wrong question. That's why. Okay, our bulk temperature is 18 and 26 over 2, which is 22 degrees. We're then going to go to table A15. And we're going to find our and finally our beta, which is 1 over. And again, we want to just make sure this is our 22 plus 273. Make sure to convert that to Kelvin. Okay, and the way this answer key is set up, and I think we should follow it, is we have also our internal convection, and here we are going to have here we're going to have a different bulk temperature. We're going to look it up. What the best way to do would be the difference between this internal temperature and the outside temperature. And in this case, we don't know the inside temperature, so we can approximate it, sorry, the outside window temperature. So we're going to approximate it just with the indoor temperature. So we're going to use okay. So the way they do it is for natural convection between two glasses, the properties. So what they end up doing is they say, assume our T of the inside pane is equal to 0 degrees Celsius. So the way we always have to solve these theoretically, as you would find your bulk temperature, and then you iterate until the temperature you guessed is correct to the temperature that you end up getting at the end. For me, I probably just would have used the 18 in this case. We don't know anything about its side. I guess we know that it's cold because we know the direction of heat transfer. But anyway, here we are. So we'll do it the way they did it. T1 plus T2, or sorry, 18 plus 0 over 2 is equal to 9 degrees Celsius. And then we're going to get all these things off table A15. We'll try to go as quickly as possible. Okay. So for a horizontal surface, so we're going to go back to calculating the outside surface. And so this is a kind of external horizontal surface. And so for that case, our LC is equal to our H, which is 1.5. Our Rayleigh number is equal So we've now looked at Prandtl number, keeping in mind this is all from our first properties. So just to ground us a little bit, this is using our 0.7304. So those are the first properties we looked up. And we'd find this at 2.787 times 10 to the 9. So now we'll look up our nuisance number. We'll use that same table we used in the last question. Last time we were doing a horizontal cylinder, and this time we're doing a flat wall. So of course the equation itself is different, but the where you get it and how you use it is the same. This is 9/16. So kind of a big equation to toss into your calculator, but not too bad. This we'd get 169.5. Going from here, H is equal to K over H. That's number. So we've looked up K, we have the window height, and we just calculated our nuisance number. So this will equal 2.858 watts per meter squared degrees Celsius. Okay, and again, we'll also calculate our area. Our height times our width, both of which were given in the question, 1.5 times 2.8. 4.2 meters squared, and we'll get our Q, H, A, T infinity minus our surface temperature. Keeping in mind, this is our surface temperature, we'll call this I. This is the one that was given at 18 degrees, and this was our 26. Okay, and this is 96. Okay, and keeping in mind this 96 watts that we calculated, this is true throughout the whole window. Again, we're assuming steady state. So at any point, if we can calculate our Q, we know it's the same throughout the entire heat transfer process. So that's going to help us calculate our inner or our outer surface temperature, or outer window surface temperature. Again, if you're a little confused by the way we're kind of doing the windows is just kind of one temperature, there's not a kind of inner outer of the outer one. It's because we are assuming that there's no conduction through the windows, which again seems a little weird to me, but here we are. So we've now calculated this heat flow, and we are just going to calculate what this would be. And so we're going to do that by finding the convection, the second mode of heat transfer. Okay. So for our inside, we're going to use our characteristic length is going to be our length of our gap. So each time we're using a different characteristic length. In this case, the T1 minus T2 refer they refer to the inner pane temperature, and this is the outer pane temperature. What's weird here is the outer pane temperature is actually what we're trying to find. But for this step, because we're still trying to do properties, we're not this is just to find H. We're going to do the same thing we did before, and we're going to do this assumption that this is 0 degrees Celsius. And again, if you were to do this for a workplace or something where the preciseness of the answer was a little more important than just this kind of example, you would want to iterate that. So you go through, this would be another spot where you could go through and guess and maybe set it up in MathCAD or something so you could do it quickly. So anyway, if we use 0 there, we're using our 18 here, our gravity, our beta we calculated, and our viscosity we looked up on the table. So everything else we should have, 18,309. Our nuisance number, okay, and so this is where we're going to use our different nuisance number, and I'm going to scroll to the section in the textbook in a second, but I'll just write it down. Okay, we have Rayleigh number, we have Prandtl number, we know our H, our height of our window, and our length. And it makes some sense that at some point we're going to want to include our height. So again, you don't necessarily need to make sense of why this equation looks the way it does, but it is good to think about kind of what you're including. So I'm just going to go over to where I got that in the textbook, or a little screenshot of it. And you can see, just like most of the rest of this convection stuff, it's just a matter of finding the right correlation. In this case, if you have this gap, which it makes sense that we would have our own section for that, because there's a lot of situations that come up, specifically with windows. And you'll notice there's actually a whole bunch. So we have for vertical enclosures, and we have kind of different H over L sections for this. All right, so in my answer key, this H over L wasn't calculated explicitly. And so just for the sake of the time, we're going to trust it, but I'm assuming that if you calculate your H over L, you would get between 10 and 40. Our Rayleigh number was between 10 to the 4 and 10 to the 7, and our Prandtl number was between 1 and 2 times 10 to the 4. So all that said, we had the right conditions to use this equation, so we go ahead and use it. And then we can find our Q. So, or sorry, we are finding our inner temperature. So we're going to do this K, business number, area. And just notice this is a bit of a shortcut. So we know our H is equal to K, business number over L. So rather than calculating their H, they just tossed it right into the convection equation. So this is the same as delta T. Okay, and we know that this is equal to 96 watts. We found that before. So this is not me calculating out this. This is from previous calculation. So if we arrange all this for T2, we would get an answer of 3.9 degrees Celsius. And this is close to 0 degrees Celsius. So according to the answer, this is close enough that we wouldn't need to repeat it. Now, my impression is that a test question might be a little more explicit about how you're supposed to calculate it to make it easier to mark. But the idea is here, if we had this far, so if we did it at 18 degrees, like I had said at the beginning, we would be quite a bit farther off. So if you were to go back and you were to take this 3.9 and you were to re-estimate all the estimations you made, you would get something slightly different, but probably pretty close to that. And you'd iterate until you got the same thing. Okay, so that's everything. I know it's a bit long, but since it's a video, you could maybe watch it a little faster or skip through it. Hopefully that's helpful, and I'll see all of you next Thursday.